First of all, Sarah, I feel bad. I got to this last year in Physics 11 with like 4 days left in class. We did this at the very end of June, which means the likelihood of you remembering much or any of this is near zero. I will be teaching it from scratch, but the notion of work and energy are fundamental to understanding physics. In fact, it bothered me enough that I didn't get to it last year that I've rejigged the whole Physics 11 course this year to make absolutely sure that I get to it next year. Generally, kids find this topic pretty easy because of the first sentence. Work is a scalar, which means the trig is going to be non-existent. Well, I will put a little bit in the homework and show you where we can bring the trig in, but I'm going to tell you right now that this test, no components. I flogged it for 2 units. This next test, no components. So generally, kids find it pretty good. The problem is every other, in fact, a couple of years ago, my class average on this was like 88 or 89, but all of them had seen the full work and energy introduction in Physics 11. You folks haven't, so I've added a couple of lessons. So here we go. The other issue is that we're using the words work and energy, and those are words that have English meanings which have nothing to do with physics meanings. When I say the word work, when you say I'm doing work, what you think, Darcy, is I'm getting tired. Work has nothing to do with tiredness. Work has a very specific physics definition. If you're doing work, you're changing an object's energy state. We're going to write that later on. But if you're doing work, you're changing an object's energy state. And if that object isn't gaining or losing energy, you've done no work on the object. Let's start out. It says this. It's defined as the product of the force component in the same direction of motion and the distance moved. What does product mean mathematically? Adding, subtracting, multiplying, or dividing? I hope so. So it's really force times distance, except I'm going to get rid of the little times sign because on your formula sheet, you might want to have your blue formula sheet handy because I'm going to give you a few hints and notes that you might want to jot on the blue sheet. That's your study guide that will help you understand the yellow sheet, which is identical, but you can't put these notes on there. And you'll see under the unit, work and energy and power, this is the first equation. Now, this is the work if you have a constant force. If you have a changing force, we've got to go something else. In fact, Marcus, you're going to get 3 definitions of work today. The first one, though, my fallback, whenever someone says, how much work? The first thing I say, well, is did they give me a force? Or can I calculate a force? We just did a whole unit on that. Did they give me a distance? What are the units? What are the units for force? Hello? What are the units for force? What are the units for distance? So technically, work is measured in Newton meters, but this is so fundamental and important, Max, that we've given it a special name. A Newton meter is a joule, symbol capital J, named after a scientist whose last name was? Okay. So, example 1 says, how much work? Okay. Does Connor do when he's lifting a 50 kilogram mass to a height of 5 meters? The first thing I would say is, okay, work equals, F equals, Mr. Dewick, work, W, equals force times distance. By the way, the letter W is going to be similar to the letter N in that it gets used all over the place. W is work. As a unit, W is watts. As a direction, capital W is west. And all I can say is, please read the context carefully. The same way N could be north, N could be newtons. In some textbooks, N is normal force. Max, that's why I always write Fn instead of N for normal force, because I want to try and avoid the confusion. I'd like you to imagine Connor is lifting, and he's lifting it at a constant speed. If he's lifting it at a constant speed, what's the acceleration? So all the forces are, I'm looking for the letter B. Balance. Okay. Without drawing, we've just finished this. Imagine the free body diagram as Connor's lifting. What are the forces acting on it? Get the obvious one. Gravity. And if he's going at a constant speed, his lifting force must be the same as gravity. Yes? So where the F is, I am going to put Fg. It's actually not Fg. It's the force the same size as Fg, but it's pointing up, which is important because I just finished telling you, Zach, that the force and the distance have to be in the same direction. If you're lifting up, and it's moving up, the force should be up. I am saying I know how big that force is. It's the same size as mg. So we can write it like this, mg, and then often for a vertical distance we call that a height. We say the work done against gravity would be mgh, which is going to be 50 times 9.8 times 5. I can do that in my head. It's going to be 490 times 5. 500 times 5 would be 2,500 minus 50. 2450? Double check me. Yeah? What that also means is that box gained 2,450 joules of energy, and Connor lost 2,450 joules of energy. Of course, we've all seen Connor shooting baskets out there. He can't lift 50 kilograms, right? Pipe cleaners, not pipes. So suppose Connor can't lift the mass straight up, but he still needs to get it to a height of 5 meters. What he decides to do is to build a ramp like that. And he's going to push this mass up the ramp. Now, I said the ramp has an angle of 30 degrees. Actually, let's try and do this as generically as possible. Let's call this angle theta degrees. What's the height he wants to reach? 5 meters. And that would be here. I'll put the h there. I'll call it height. In this specific example, 5, but generically. And then, what's the distance that he's traveling? Well, that distance would be that, which I think is actually the hypotenuse of this triangle. Is that okay, Sydney? Let's do a little trig. This letter H, this height, opposite, adjacent, or hypotenuse. Opposite. And I feel bad because the D is the hypotenuse, and I've got two H's in the same diagram. One H stands for height, one H stands for hypotenuse. I've changed colors to try and make it obvious, but you've probably heard me say this, and if not, you're going to hear me say this. We need more letters in the English language. We're just running out. Hence the N and the N and the N and the W and the W and the W, running out. Which trig function? Sine? So sine of theta is the height of the ramp divided by the distance that the ramp is long. I want to get the d by itself because work equals force times distance. How would I get the d by itself? Right now it's in the bottom of the fraction. I don't like it there. How would I get it to the other side so it's on the top? Yes? Multiply. Can you just imagine that? So the d is now on the top on the other side. There's also a sine theta. How would I move the sine theta over? Can I argue then in one step in our head that d is the height divided by sine theta? Is that okay? My grade 11s are just getting into the formula manipulation thing, and I still have a few of them bucking and resisting and wanting to stick in numbers. I wish I could show them the future and just say how much better it is if you wrap your brain around it. But thank you. Draw the line over here. So we said work equals force times distance, yes, but what's our distance expression this time? H over sine theta. You okay with that, Christina? Now, the force and the distance have to be in the same direction. Otherwise, you're not doing work. The force and the distance have to be in the same direction. Otherwise, you're not doing work. Now, this distance is along the ramp, so the force would have to be, listen close, parallel to the ramp. What force do you think that would be, based on the unit we just finished? Parallel to the ramp. Luke, what? Now, what we're actually going to say is this. The force that he's pushing up with is a force. It's an applied force. But if he's going at a constant speed, it must be exactly the same magnitude as mg parallel. Is that okay? So I'm going to say the force is mg parallel, except mg parallel is mg two lines, which is, let's write over here, mg sine theta. if you can wedge it in there. That is force times distance. Ooh. Does anybody notice something kind of cool? What happens to the sine thetas? Yeah, one on top, one on the bottom. It's sine over sine, which is the same as 1. So you actually end up with which is the same expression I had right there. The ramp does not save you work, but here's what happens. It saves you force. You don't have to push as hard. If you made the ramp 10 meters long, the force would only have to be half as big as lifting it 5 meters straight up. If you made the ramp 15 meters long, I don't know what angle you'd put it in, but you could calculate what angle. If you had to push it 15 meters, you've reduced the force by a factor of 3. This is how ramps work. They don't lower the amount of work, but by increasing the distance, you can decrease the force, because work is force times distance. In fact, a ramp is an example of what we call a simple machine. It reduces the amount of force required, but the trade-off is whatever fraction you reduce the force by, you increase the distance by that same factor. The amount of work remains the same. In fact, that example that we just did proves it algebraically. When we actually brought in all the thetas and did it generically, we still ended up with mgh. But now we go to riding a bike, and I have to be careful because I did this with my last class, and it turns out I made the assumption that at 6-year-old they were smart. At age 6, they were smart, and they were not. So, here's the question. Put your pencils down and look up. You're riding a bike up a hill, a steep hill, and the hill is 300 feet long. This is from the US. You know what? Make it 300 meters long. It's steep enough that you can't pedal straight up. So what do? You zigzag instead. And this is where I blew my kid's mind. My block F students had never clued in that it's easier to go up a hill if you zigzag. Have you figured out when you were a little kid that to go up a hill you can zigzag and it's a lot easier? Darcy has figured that out. Thank you. You're smarter than my 1 graders from the last class. Okay. Now, if I zigzag and my path ends up being 600 feet long, what happened to the average force that I had to exert? 1/4 as big, 1/3 as big, half as big, or the same as before? If I double the distance from 300 to 600, what happens to the force? Half. Because I'm stuck with the same amount of work. It's still mgh. It's still mg times 300, or I can make it a 600 and lower the force. So I'll do the same. It'll be half as big, but it's going to be the same amount of work. Okay? And you figured that out when you were 6 or 7. To go up a hill, you zigzag. Sure. Increase the distance. By the way, that's all a stairway does. We have a choice. All of our stairs could be vertical ladders. That would be a much shorter distance, but you would be physically having to pull your own weight up the entire time. Or we can make it at an angle, increasing the distance, dramatically lowering the force. Is that okay? Simple machine. So I should point out in the real world, Sarah, there would be friction. So if you're pushing up the ramp, friction would be exerting a force down the ramp. So you end up doing slightly more work than you originally did. But I'm telling you, the force is still significantly smaller. The pyramids were built with ramps. As far as we know, the Egyptians did not have the wheel, or at least not in their building. But you can run the numbers. It's very doable. Aliens didn't build the pyramid. You can run the numbers. It's perfectly feasible for human beings to have done it in about 25 years, which matches with the records shown for the building of the pyramids. It's actually a neat little calculus problem that we used to solve. Next page. Example 3. Who am I going with here? We'll go with Justin. This is going to be your cue for about the next 3 weeks. You ready, Justin? Work is what times what? Work is what times what? And you're going to say force times distance. Work is what times what? Work is what times what? Now, the conditions that I put on that, where the force and the distance had to be in the same direction. So here's our thought question. I have a mass on the end of a string here. I'm whirling it around my head in a circle. There is tension in the rope. I can feel it through my wrist, and tension is a force. Are these balls moving through a circle through a distance? Yes. So the question is, am I doing any work? Let's find out. Justin, work is what times what? But we said the force and the distance had to be in the same what? Direction. So tension is in that direction because it's along the rope. But Zach, I'm going to argue the distance that it's moving is in that direction. How much work am I doing? So easy that it's tough. How much work am I doing? As a number, please. 0. 0 joules of work. If you're at a right angle, no work. What that means, by the way, is the normal force, which is a force, never does work, because the normal force was defined as always being at a right angle. In general, a force in the same direction as the motion, we call that positive work because the object gained energy. A force in the opposite direction of the motion, we say you're doing negative work. The object is losing energy. It's not a direction, it's not a vector. Gain and loss are magnitudes, not directions. So work can be positive, you gained energy. Work can be negative, you lost energy, but that doesn't imply a direction. What if we exert a force at an angle? Did I say angle? What? Yeah. I'm going to give you some in the homework with components. I'm not going to give you any on the test. I flogged it to death. But for what it's worth, here's a little kid with his wagon, and you can see we have a force up. You know what? Let's draw it a bit bigger. We have a lovely force up at an angle theta. Here's our mystery force F. The distance that this wagon is traveling is very clearly, Christina, horizontal. So what I need is a force that's horizontal. There's the H that I was going to go with, which we called, I think, Fx. I could draw Fy in, but since it's at 90 degrees, honestly, for this diagram, I don't care about it. I know it's there. Who cares? Fx, opposite, adjacent, or hypotenuse. And the force that we have, hypotenuse, which trig function? Of course it is. So the actual formula, and I did not put this one on your formula sheet, but if you take physics in post-secondary, work is actually force times distance cos theta. Except, get your calculators out. What if theta is 0 degrees? What's cosine of 0? 1, and you get force times distance, which is Justin's equation that I've been... In other words, if you're in the same direction, you can ignore the cos because it's just a 1. Force times distance. What if the force is this way and the distance is the opposite direction? How many degrees is there between my two pointed arms right now? 180. What's the cosine of 180? It'd be really cool if that ended up being -1, and if that was what gave us a negative force. Oh, sorry, negative work. Is it? Oh, it's kind of cool. Oh, and what's the cosine of 90 degrees? What about the normal force? It'd be kind of neat if that just gave us a 0 and forced us to say that does it? There you go. So that's not on your formula sheet because you can kind of derive it from components anyways, but I don't think on your test, I know in the ultimate review there are a couple where you might have to pull out the components. Okay, but I don't think I'll be giving any like that on the test. Justin, work is what times what? That only works for a constant force. What if the force is not constant? You might recall, Marcus, I think you were the one that I said this to. We're going to end up with 3 definitions of work today. And it's a sequence that you go through. If the question says, how much work? First thing I look for, Justin, is times distance. What if the force isn't constant? What if it's a changing force? Well, it turns out work is also the area under a force versus distance graph. So, question A off to the side here says, here is a force versus distance graph. Force in newtons, distance in meters. I sketched this very roughly. How much work is done in moving this object from 2 meters to 6 meters? Well, 2 meters, right about there. 6 meters, right about there. I can't go 3 times 6 because, Zach, the force is changing. It starts out 1 Newton high, but it ends up becoming 3 newtons high. The force is changing. Okay. So, it's also that area. What shape is that I've just kind of traced out? 2 parallel sides, 2 non-parallel sides. It starts with letter T. Trapezoid. It's trapezoid. Do you know the equation for the area of a trapezoid? There is one. For a candy, does anybody know? Because it's nerdy, but it's out there. Yeah? Divided? Don't think divided by. By the way, the reason we don't make a big song and dance about it, Alex, is it's redundant. You can survive just fine without it, because any trapezoid can also be divided into a rectangle and a triangle. You meant that? There's actually an equation. It's 1/2 bracket A plus B close bracket times the height, I think. So, how much work is done in moving this object from 2 meters to 6 meters? We're going to find the area of shape Roman numeral 1, which is a rectangle. I will not give you the equation for the area of a rectangle. How do I find the area of a rectangle? Something times something. Okay, so let's go LW. What's the length of this rectangle? Don't say 6. 4. What's the width? 2. In your head? 8. Then I'm going to find the area of the triangle. I was nice. I actually put this equation on your formula sheet. It's on the same section where there's pictures of triangles and the quadratic formula and stuff. But I'd like to pretend that maybe you know this. How do you find the area of a triangle? It's base times height divided by 2. Yeah, it's half a rectangle. That's really what it is. It's just we call it a base because that makes a bit more sense because it's not exactly a length. But yeah, it's base times height divided by 2. What's the base here? 4. What's the height here? Careful, don't say 3. What's the height of the triangle? 1. Divided by 2. In your head, Elliot? 2. And so if I want to find the total work, 10 joules. That's how much work it took to move this object from 2 meters to 6 meters. What that means is this object gained 10 joules of energy. Why? Because energy is the ability to do work. The ability to exert a force over a distance. If you have the ability to do that, you've got energy. There are many forms of energy. One of the ones we'll look at the most is the energy of motion, which we're going to call kinetic. There's also heat, which is created by friction. That's another form of energy. We'll look at that a little bit. There's a whole category called potential energies. Potential means stored energy. As an example, this battery has stored electrical energy, electric potential energy. One of the most common ways to store energy is what we call gravitational potential energy. This is the energy an object has due to its height. This is the energy an object has due to its height. I won't hurt you. If I dropped this, would it exert a force over a distance? Can it do work? Yes. Does it have energy? Yes. Ugh. More energy or less energy? More. You know what? I'll bet you the equation might have an H in it. Probably has an M in it as well. Because I am going to do this one. If I drop this, does it have energy? Yeah. Will it exert a force over a distance? Yeah. Very big force? No. I'll bet you the equation for stored gravitational energy will have a height in it, and I bet you it'll have a mass in it. Make sense? Thank you for being my guinea pig. There's also chemical potential energy, gunpowder, stored energy. Food contains chemical potential energy. It's why you eat. Other forms, sound is a form of energy. Elastic energy, when you stretch an object, you've gone force times distance. You've stored energy in there, and that energy can be used to do other things. Nuclear energy, many types. We're primarily going to be looking at two, kinetic and potential. We'll write that down later. Example 5. Sometimes when we do work, we make things move. Fill in the proof below to find an expression for the energy of motion, kinetic energy. I'm going to use Ke for energy, which is technically wrong. Technically, you should either use a letter U or a letter E. I'm going to go with Ke, and you'll see later on this year why I do that to avoid confusion. But it is wrong to use two capital letters for one concept. Sue me. It'll be clearer. All right, let's generate an equation for the energy of motion. We're going to start out with the definition of work. Justin, work equals what times what? Let's write that down. Oh, and F equals what? Dasha. So I can write this as MAD, force times distance. Are you mad? No, that's just the pops up there. And then I'm going to get clever. You'll see why in a second. I'm going to write this as 1/2 M2AD. I've multiplied by a 2 and a 1/2 at the same time. What have I really multiplied by doing that? 1. So have I changed anything? No. You with me so far? Why did I do that? Since VF squared equals VI squared plus 2AD, can you get the 2AD by itself in that equation? What does 2AD equal? Can you get the 2AD by itself in this equation? What does 2AD equal?
VF squared minus VI squared.
And that's what I put right there. Oh, and if we start from rest, what's VI?
0.
So if VI equals 0, here is your equation for kinetic energy, 1/2 M V squared. That is how much energy an object has if it's moving. It depends on its mass. Heavier objects have more energy. And it depends on its velocity squared. Little side nerd note. So 1 joule of energy is not very big. A typical jelly donut has about 10 to the 6th, about 1 million joules of energy. A very small way to measure energy on the atomic scale is in ergs. 1 erg is about the equivalent of a mosquito doing a push-up. Yes, I ran the numbers. It's about 10 to negative 13 jelly donuts, or about 10 to negative 17 joules. A joule is not very big. You're going to see in our examples, we're often in the tens of thousands or hundreds of thousands of joules. Well, even just lifting 50 kilograms up 5 meters. What was it? Something like 2,450 joules, which... Okay. So, a golfer wishes to improve his driving distance. What would have more effect? Making the club twice as heavy, doubling the mass, or doubling the speed with which the club head strikes the ball? And convince me.
Would it be the speed if you're squaring it?
What?
You're squaring the speed, so it would be the speed, right?
Absolutely. If you double the mass, you'll go twice as far. If you double the speed with that squared, when you square the two, what does it turn into? That right there explains most sports science over the past 30 years. Any hockey players here? Last 30 years, Luke, have hockey sticks become heavier or lighter? Yeah. Now, it's a trade-off because there is an m in the equation, and so making it lighter, you are losing that, but that's squared. The bang you get for your buck is so worth it. The fact that if it's lighter, you can make it go faster, oh, we'll take that. Golf clubs have become lighter. Tennis rackets. I played a lot of tennis when I was in high school, when I was your age, and then I stopped for a while. I was in a sports store a few months ago, and I picked up a tennis racket and just swung it for fun. It felt like a feather. Wow! Well, yeah. It's all about club head speed. It's all about racket speed. It's all about stick speed. Because of the squared. Because of the squared. That squared, although you don't realize it, dominates your life in many ways you have yet to realize. Preview of coming attractions after Christmas. I will be giving out a bonus video game. Sorry, a bonus toy, not a video game. A bonus toy assignment. You may have seen some of the grade 12s playing with it last year. And the challenge that I give them is to get to 10,000 RPM. But what they don't realize is that equation has a squared in it. Getting to 9,000 RPM is fairly easy. Getting that extra 1,000 because of the squared, it's not just, oh, I need an extra 10% to get to... No, you need way more. Hey, you know what? Sometimes when we do work, we lift an object and we give it height energy. Fill in the proof below to find an expression for height energy. Also called gravitational potential energy, or PE for short. Justin, what's the definition of work? And if you're lifting it, you're lifting the same magnitude as gravity, and we called that a height. We actually derived that in the very first question. Gravitational potential energy is given by mgh, which confirms what Justin suspected. I told you, I'm pretty sure it should have an h in the equation, because higher gave it more energy, and it should have an m in the equation. And yeah, I guess it should depend on what planet you're on. G, 9.8. On the moon, 1.6. On Mars, whatever Mars is, 3 point something. Okay. That G is 9.8. Why not negative 9.8? We're in scalar. Who cares? Usually, we're going to be focusing on what we call mechanical energy, which has two main types, kinetic and potential. We'll bring heat in occasionally. Okay? This brings us to what we call the Work-Energy Theorem. This is important. You maybe even put a little star next to this. I don't know. It's on your formula sheet as well. Justin, work is what times what? What if the question didn't give me a force and didn't give me a distance, but it still said find the work? Well, then I would go looking for a force versus distance graph, because I know it's the area under a graph. What if the question didn't give me a graph? There's a third definition of work, and this is the procedure, Sarah, that I go through. I look, force times distance? Nope. Graph? Nope. Okay. The third definition of work, which is the best definition of work, but also the most complicated one, is what's called the Work-Energy Theorem, and it says this: if you want to know the net work done on an object, it's equal to its change in energy. It's equal to its change in potential plus its change in kinetic. Where change in anything is always that little part is not on your sheet, I'm going to expect you to commit that part to memory. But the W equals delta PE plus delta KE is on your formula sheet. Some textbooks, and I think this is sloppy, instead of saying that the work-energy theorem is the change in potential plus the change in kinetic, they assume you're on level ground. If you're on level ground, what's your change in height? 0. So what's your change in potential energy? 0. So some textbooks just say this. But Max, that's only true if you're on flat level ground. It's not universal. Put your pencils down, look up. All right, example 8. Sydney, what's example 8 want me to find? How much work? Pause. Justin, work is what times what? Sydney, look at the question. Do you see a force in newtons or do you see a distance in meters anywhere in that question? Loud and proud. So I can't use that method. This is our procedure. So it says, how much work? First thing I try, force times distance. Does that work? No pun intended. Okay. Oh, it's also the area underneath a force versus distance graph. This is meant to be Captain Obvious. Do you see a graph? Okay, so we're going to go to our third definition, the work-energy theorem, which says work is equal to the change in potential plus the change in kinetic energy. Now, if I gave this to you on a test, I would make it very clear that this was on level ground and there was no change in potential. But I'll say to you, does this question mention a hill or anything like that? So we're going to argue that your height isn't changing, and since your height isn't changing, your potential energy isn't changing. What's changing anything? So this is going to be KE final minus KE initial. Sydney, what's the equation for kinetic energy? It's on your sheet, and we wrote it a couple of boxes ago. Had a 1/2. It was something. What was it? Yeah. It's on your sheet. You'll probably memorize that one out of laziness. So KE final is going to end up being 1/2 mv final squared minus 1/2 mv initial squared. Are any of these 0? Sasha, which one? Oh, so I can do this. It's going to give me 0 minus. I am going to get a negative answer, which I should, because the negative is telling me, oh, you want to stop that car? It has to lose energy. Otherwise, it ain't stopping. And it's going to be negative 0.5 times 1200 times 32 squared. Negative 0.5 times 1200 times 32 squared. Times, Mr. Dewick? Do you get negative 614,400? I'll go to 3 sig figs. Negative 614 and then 3 zeros. And that is joules. Now, Justin, what's our first definition of work? What did we just find, Sydney? Work. What's the other definition of work, Justin? If I knew my braking force, if I knew the force that my brakes in my car could exert, I could figure out the distance it would take me to stop. It would be take this number and divide it by the braking force. Suppose you're going twice as fast. How much more energy will you have? 4 times as much. So how much more distance will you need to stop if you're going twice as fast? 4 times, and this is for you, my young, stupid drivers, all of you are. If you're going twice as fast, it has nothing to do with your skill level. Physics says you need 4 times the stopping distance. What if I was going 3 times as fast? How much more stopping distance would I need? 9 times as much. 9 times as much. Let's get a little morbid but a bit serious, and we'll try and do some preventative teaching. Instead of thinking about it in terms of stopping distance, let's think about it in terms of damage done to the occupant. If you are in a car accident going 20 kilometers per hour versus a car accident going 80 kilometers per hour, 80 divided by 20, 4 times faster, squared, 16 times more damage if you're in the 80. 20 kilometers per hour versus 100 kilometers per hour, 25 times more damage. And so my message to you is, and I'm speaking mostly to the guys here, has nothing to do with your driving prowess. Well, I can stop. No, I'm sorry, the laws of the universe, that squared acts up in ways you don't think. Slow down, please. Especially when it's raining and mu just got smaller, and so your braking force, your maximum braking force, just got dramatically smaller. Slow down. End of rant. Nate, what's number 9 want me to find? Amount of what? So the first thing I would go is work as force times distance. Do you see a force in newtons or a distance in meters? Now I do see a distance in meters. Do you see a force in newtons kicking around anywhere? Sure, no. Right? You're looking at the numbers. I don't see newtons anywhere. Do you? No. So, do you see a force in newtons? No. Now you could argue mg, but wait a minute. Is there also a speed? You know what? We're going to use the third definition of work, the Work-Energy Theorem. The minimum amount of work is going to be the change in potential plus the change in kinetic. Nate, what's change in anything? So it's going to be PE final minus PE initial, and then plus KE final minus KE initial. Change in plus change in. Are any of these zero? Let's do the kinetics first. How fast are we moving at the top? Nate? So that's not zero. How fast are we moving before launch? What's our initial velocity? Sorry, initial speed? What's our initial kinetic energy then? Okay. Now, potential energy is mgh. So really we're asking is, when is the height zero? When is the height zero? Final or initial? Which one? How do you know? Well, because it says at the top of its arc it reaches 245. That sounds finalish to me, okay? Yeah, I mean, PEI, it's not a real province, right? We know that. Sasha, the premier isn't a premier. They're a mayor. Let's be honest, right? I'm the premier of PEI. No, you're a mayor. It's just a big city. Throw a little shade there, Mr. Duick. Trying to give you a stupid way to remember some of this stuff. Okay. So, we can go a little further now. What was the equation, Nate, for potential gravitational energy? It's in the box and it's on your sheet. I think it's on your sheet. Yeah. Look at your formula sheet, please, because that's where you're going to find it on the test. Yeah. You way overcomplicated that. And this is final, so it'll be H final. Yes? And there's a plus sign. While you're there, what's the equation for kinetic energy, Nate? And so what's the equation for kinetic energy final? A half mv v squared. Here we go, plug and chug. M 19, G 9.8, 245 plus 0.5, M 19, V 95. What do you get? this on your calculator. I think you get something in the 100,000s, I think. I'm going from memory. I didn't do that one in my head. What'd you get? 131,000, and then some more. We'll go to 3 sig figs. 131,000. Nate, the reason, by the way, that I said minimum amount of work is this isn't accurate. You would also lose some energy to the air molecules you were bumping into, and to heat, and to sound, but you need at least that much energy in the gunpowder that you're using. Don't turn the page yet. Mr. Dewick. Yeah, Elliot. What word is in front of the word speed? Elliot, what word is in front of the word speed?
Horizontal speed.
What word is in front of the word speed? What single word is in front of the word speed?
Horizontal.
There we go. And that 255 meters, Mr. Dewick. Yeah, Elliot. That's a height. A height would be, I'm looking for a word that begins with letter V.
Vertical.
Gotcha, Mr. Dewick. You have yelled at us all year, and you have said, don't you dare put a horizontal and a vertical in the same equation. And there you are, Mr. Dewick. That 245, that's vertical, and that 95, that's horizontal, scalar. Okay? That's one of the beauties of work and energy. You can be a lot less fussy and meticulous than you were, because it's a scalar. It really doesn't care. Were you thinking that? Nod your head. Yeah, there you go. Sure. Last one. Call me silly. I'll bet you for this one we're going to be using that graph method, because I said there was 3 ways to calculate work. I have a feeling here, force times distance, nuh-uh, and I have a feeling, okay. All right. Luke, what's example 10 asking me to find? How fast? Speed. Yeah. I love the fact that you said speed and not velocity, because scalar. What? What did they give me? A graph? What kind of a graph? What's on the y-axis? What's on the x-axis? This is a force versus distance graph, which turns my thoughts to work. Okay? This is going to seem silly, Charbel, but we're going to write this. Work equals work. Yeah, Captain Obvious. No, and we're going to use 2 different definitions. We're going to use the definition of work that had a speed in it, which was change in potential plus change in kinetic. We're going to keep working on the right-hand side here and just dropping the equal sign down. I like example 10, I like example 10, I like example 10. Example 10 is a nice question. Although if I gave this to you on a test, I would say starts at rest and stays on level ground. I forgot to include that here, but I am going to argue, Luke, this doesn't mention a change in height. We can do that. Drop your equal sign down again. Luke, what's changing anything? You thought it right, even though you said it wrong twice. Knifus trius. It is hard to say, and I don't know why, but you're not the only one that, Are any of those 0? Is your speed ever 0? Because kinetic energy contains a V in it. Okay, so we can even do this. So on the right-hand side, Luke, I end up with a half mv final squared. Now, why is that nice? Because you told me we were trying to find v. Let's go back to the left. How else can I find work? It's also the area underneath a graph. Now, we want how much work starting until we get to 0.8. So we want that area. That shape is not a trapezoid. What shape is that? Triangle. What's the area of a triangle? So I'm going to go base times height divided by 2. And now I'm going to go more specific. I've scrolled down, but for your triangle, how long is the base? 0.8. How high is the height of the triangle? 16. Divided by 2, which is what? Oh, I can do this in my head. It's going to be 8 times 0.8. 6.4, I think. Double check me, but I'm sure I'm right on that one. Yeah? Okay. See, we're being clever here. We're using 2 definitions of work. Yes? Luke, what did you say we're trying to find? How would I get the V by itself? What do I do with the M? What do I do with the 1? Who cares? What do I do with that 2 that's in the bottom of the fraction there? What do I do with this 2 right here? What's this 2 doing right now in the bottom of a fraction? So how will I move it over? I'm going to say, dividing was a bad guess, right? So are you telling me that, first of all, the 6.4 drops down like a domino? But you said I'm going to divide by M and multiply by 2. Now that would give me, Luke, VF squared. Now we're in happy physics 11. How do I get rid of a squared? There you go. 2 times 6.4 divided by M, 25. Square root. That's the speed. What do you get? By the way, Charbel, think about what we're doing here. I don't even really know what's happening. I don't know what we're pushing. I don't know what's going on, but I can tell you how fast this object is moving based on the data they gave me. It must be moving this fast because that energy had to go somewhere. If it didn't go into changing the height of the object, it went into changing the speed of the object because work means you're changing an object's energy state. What'd you get? I think it's 0.7 something something, isn't it? 0.716 meters per second. Justin, work is what times what? It's also the area under a... By the way, why couldn't I just go 16 times distance? You can see, I hope, the force is changing. It's getting bigger the whole time, so you can't use force times distance. It's also the area under a force versus distance graph. It's also the change in potential plus the change in kinetic, which is the most useful but also most writing one. What's your homework? Number 1 is good. Number 2 is good. I must have deleted number 3. 4 is good. 5 is good. 6 is good. You can skip 7. 8 is good. Nice stretch. 9 is good. Okay. I have not done 10 with you. See if you can figure it out. You can skip 11. 12 is tricky. Mr. Duick, it says 3V. I thought you said 9 times more energy. That's if we're starting at 0. Here we're starting at V. $13 is good. Skip 14. 15 is good. And there you go, my children.